Good evening, everyone, and welcome to the sixth session of the course Introductory course in Real Analysis. So, in today's session, we'll be mainly talking about series. So, we'll be solving problems related to series, its convergence, and all. So, to begin with, let's start with this problem. So, the question is that suppose we have been given a series of non-negative terms. Okay, so that means each an over here is greater than equal to 0. Okay, so you have a series which is convergent, so it's given to you. Now you have to prove that this series root an into an plus 1, this series is also convergent. So this is what you have to show. Okay, so now to show this you have to use the fact that summation an is finite. That means the series summation an is convergent. So how do you think that how can it be solved? So I think I mentioned in the last session as well that whenever you have to prove something is convergent, okay, so over here it's very clear that you cannot use any test as in root test or ratio test and all other kinds of sorts. So the only thing what you can think is, okay, we can do some comparison, right? Comparing with what? Comparing with the things which are given to us. So it's given to you that the summation an is finite. So you have to compare this term with an in some sense, right? Then you can hope that okay, then we can prove the convergency of this series. So do you know any sort of inequality or upper bound for this term? Do you have any idea of some getting some upper bound for this? Okay, so I'll write an inequality which is very obvious to prove, but let me see if you know or not. So suppose for, let me choose positive. So for AB greater than 0, root over AB is less than equal to A plus B by 2. Have you seen this inequality?
Yes, sir. Arithmetic mean is greater than the geometric mean.
Correct, right. So do you know the proof? Although it's very obvious, like there's nothing much to do. So this is the geometric mean and arithmetic mean relation. Correct. So the proof is quite easy. So I'll just write one line. It's one line proof. So see, proving this is equivalent to saying like you just do the cross multiplication. You will get a plus b greater than equal to 2 root a root b, right? And this is nothing but, you can check, this is root a minus root b whole square greater than equal to 0, which is true, right? This square is always non-negative, right? So this is the proof of this inequality, which is very obvious. Okay, so now using this, like we have to prove that this series is convergent. Now I think the proof must be very clear to you. Now you can do the proof, right? So it's very simple. So you just have to do an times an plus 1 less than equal to an plus n plus 1 by 2. And now, okay, so all are positive, so this is less than equal to, right? So now you have, so you know, and summation an plus 1 by 2 for n equal to 1 to infinity, which is half summation an plus summation n plus 1 to infinity, right? Now you know that this series is finite and this is finite, so you get, so this is finite. So by comparison test, this series root an plus 1, this is also finite, right? Is this okay? So this is a very easy
Yes.
problem. Yeah. Okay, then if it's okay, let's proceed further. So in the second question is basically the converse of the first one. So over here you have been given that okay, this summation root n times n plus 1, this is, suppose this series is convergent, then the question is that will this imply that summation n is finite or the series summation n is convergent? Can you say this? What do you think? The first thing is, what do you expect? Like, do you think that it should be true or should be false? Suppose you have some, so what should I say? So look at this term. So the only thing what you can think of is, okay, let's try to compare it, right? There is no other way, correct? So you have this, you know that this is finite, and on the left side you have an, right? So you want this kind of bound. This is the kind of bound you want to look for. If you have such bound, then you are done. There is nothing more to be done. But over here you see this an plus 1. If you want to replace, you need to assume. So suppose I assume an plus 1 is greater than equal to an. Then it's obvious. Then this is true, and then you can prove that it is convergent, right? That means if I include, okay, so this is I guess the next problem. So if I have some condition like this, then it's very easy problem. Then you are through. But in this situation where you have nothing assumption, you have no assumption on the sequence an, then how can we deal with this thing, right? And the statement what it is, that this statement is false. Okay, so the statement given to us over here, so the answer to this question is that this series will not converge. So the answer is no. Okay, now when I say like the answer is no, then at that point you have to look for some counter example, correct? So you have to find some example such that this series converges but this does not. Okay, so better to start with the sequence such that the series summation n is not convergent. Then we'll see if this is, how can we make this convergent, this one. Okay, okay, so now let's try to find the example. Okay, so the easiest one, what you know, or the what you have seen so far. So if I take, so this is just to get the idea. So suppose if I take an to be 1 by n, okay, then what do you think? So this is clearly summation an is divergent, so this is infinity. But if you look at an times n plus 1, this is root n, sorry, 1 over n times n plus 1, right? So it behaves like 1 by n only, correct? Because this is just, so this is nothing but, if you want to write it precisely, this is 1 by n square plus n. And now if you want to do some test, okay, so you can even write this as this. Okay, so what you can do is you can write it as 1 by n, and then you have 1 plus 1 plus 1 by n. So I am taking n square common, then I will get this thing, right? Okay, so this is root an times n plus 1. And now if you sum it up, then you can see, you can either you can do some comparison test. Okay, so you can compare this sequence by I mean, if you want to use the series test, so maybe you can write an as root 1 by n square plus n, and you take bn to be 1 by n square or 1 by n. If you use the comparison test, you will see that this series is divergent. Okay, so I am saying just check using this type of thing. That's why I said that this behaves like 1 by n. Okay, in that way I am saying. So you can check using this that okay, this series is divergent. So this is not the correct choice. So this example is not going to help us. Okay, so again we'll try to use the trick what we used in the last session. So I said like let it to be even and odd, like this kind of situation if you do, then the things get better. I mean, then you can get actually the counter example. So now what changes, what I'll do, so see, this was my earlier example which didn't work. Okay, so this one didn't work. So now what I'll do, So I'll define the sequence, the an term, nth term as, so what you do, so I'll see this is very helpful to make this divergent. I mean, so 1 by n I'll try to keep it so that I get some divergence criteria, so that this condition can be fulfilled. So see what one can do is I'll define 1 by n, okay, when n is even, let's say, or odd, whatever you feel. So when n is odd, let's say, okay, and now when n is even, so n is odd means n is equal to 2m plus 1 for some m, right? When n is even, let's say n is equal to 2m, then you just define 1 by n square, okay. Again, if you do summation an, because of this term, so see what will be the sum, n equal to 1 to infinity, then you will write summation an when n is odd, right, n odd, plus summation an when n is even, right. In other words, what you will write is 1 by so I should write here 2m minus 1, okay. So m belongs to natural number, n belongs to natural number, okay. So this can be written as 2m minus 1, where m is from 1 to infinity, plus this you can write it as 1 by 2m, where m is from 1 to infinity, sorry, 2m square, right. So this, you know that this is finite, so if you want you can write it as 1 by 4m square, right. So this, you know that this 1 by m square is there, so this is finite, but this term is divergent, right, because this is behaves like 1 by n. So this sequence, this series summation an is divergent, right. So this series is divergent. So this was possible because I included this one as before. So earlier I just chose 1 by n. Now over here I have done some mixing. So I have chosen two terms, like different types of alternatingly I am choosing the terms, okay. So in this fashion, so now this summation n is still divergent. Now let us try to see what happens to summation root n times n plus 1, okay. So let's look at this term an n plus 1, n is from 1 to infinity, right, okay. So now let us see what it turns out to be. So this is root an is 1 by n, okay. So how should I write it? So let's write it in this fashion. So an I am writing it as a2m, okay. So n I am choosing as even, and the next term would be odd, right. So I am fixing n equal to 2m, or should I do other way around? So you just do other way around, so that this becomes the odd. So a2m minus 1 and a2m, correct. This is the combination. So you see over here you have, if you write, what is this? This is root a1 a2 plus a2 a3, okay. So over here you have to include one more thing. So this is from m equals to 1 to infinity, and then here also it's m equal to 1 to infinity, and now you will write first the odd term, which is a2m. So over here it's a1 a2, and then you have a2, so m, yeah, 2m plus 1, okay. So what I have done is basically this one. So let me precisely write what I have done. So see, look at this term, okay, this one. So what is this? This is root a1 a2, root a2 a3, root a3 a4, root a4 a5, okay. This is how these terms are. This series is given in this form. What I am doing, I am writing these odd terms first, I mean which one starts with odd, okay, and then the next term, which is, so these terms, these two terms are considered here in the first one, and the one which starts with even, like a2 a4, then these two terms are being carried over here, okay. So this is how it has been written, okay. So this is just another way of writing this, and why I am writing this, just to put the value of ans, like what my ans are, because ans are given in this form. So I have to first write this sequence, this terms in terms of odd and even subscript, right, like this. Okay, so that's the simple reason to write this in this way. Now now what is the difference from the previous case? If you look at the difference, I have included a higher power over here. So now when it, so if you look at the earlier case, it was 1 by n and 1 by n kind of thing, right? So it was turning out to be like 1 by n, correct, if you notice the previous case. But now what I have done, so here it's 1 by n, the other one is like 1 by n square. So now if I take root, so I'll get 1 by n 3 by 2, and then it will be convergent. Did you get the difference? The difference lies at this point. So I have included this term so that the power will increase by, so it is now, it won't be just n square, but it would be not just n, but it would be a bit higher, and precisely it's 3 by 2. Okay, so now let me complete this. So over here you have, so for odd terms what I have is the same as the, so 1 by 2m minus 1, and for the even one what I have is 2m square, so 4m square. In a similar way, over here I have 4m square, and over here I have 2m plus 1. Okay, so now what you can do is m is equal to 1 to infinity. Over here you have 1 by, so 4 you can take out, so maybe I will write 1 by half, and then you have m square, and then 2m minus 1. Here again you have half, summation 1 by m square 2m plus 1. Okay, now I'll just try to use some bound just to simplify it. Otherwise over here only you can understand that, okay, now it's convergent, but just to complete it I'll just try to write it in a better form. So you see 2m minus 1, okay, this is greater than equal to what should be 2m minus 2, right? So I can write this one as 1 by m square, 2 I will take common, and then I will have m minus 1, right? So, and over here similarly I will have summation root over 1 by, so over I will just simply, so 2m plus 1 is greater than equal to 2m, okay, so I am using that, so I will have 2m cube, right? So now what one can do is, okay, I think here also you can do one more thing. Okay, I will do this. So again m is greater than equal to m minus 1. Okay, so here only I should replace this. Okay, just let me, okay, so here I'll just replace m minus 1. Okay, so I have replaced m by m minus 1 and 2m minus 1 by 2m minus 2. Okay, so these are the bounds that I have used. So these two are used in the first term, and this one is used in the second term. Okay, fine. So now what I have is 1 by 2 root 2, and then you have summation m from 1 to infinity. We have here 1 upon m minus 1. Okay, there is a bit of problem here. Okay, so you, because here you see if I start with m equal to 1, then this becomes 0. Okay, so this is not a good bound. So what I can do is I'll start from m equals to 2. Okay, so let me, just to avoid that, okay, because I am using some bound which is not a good bound for this case. So for m equal to 1, I'll just put as it is. So I have 1 by 2, I'll put m equal to 1. So here I'll have root over 1 by 1, and this is also 1, right? Correct. So I'll have m equal to 1 if I put, so I'll get 1. So it is basically half, 1 by 2 times 1. So this is for the first term, and then this is from m equals to 2, and this is for, so over here you have m equals to 1 to infinity. Okay, so because one term does not matter much, so I have just separated it out, and then I have this. So now you can easily check. So this is 1 by 2, and over here I have this 1 by 2 root 2. Okay, again here you can do a kind of change of variables. So let's put k equals m minus 1 over here. So what you get is 1 by k 3 by 2, and k is from 1 to infinity, and again the same thing you have here, 2 root 2 summation m equals to 1 to infinity 1 by m 3 by 2. So here k is equal to m plus 1, m minus 1. Okay, so now you know that this is finite, this is finite, correct? So this whole thing is finite, right? So again, like the previous class, like I am using this odd and even type of thing to introduce two different kind of sequences. One is divergent, the other one is convergent. Okay, like if you look at independently, so if you look at this term independently, it is divergent, this term is divergent, is convergent. So this summation n is divergent. Okay, now but the product, the way we have taken product, see here the main difference is one is odd, one is even, like this kind of situation is there. That's why we have introduced this n is odd, n is even. Okay, so that when I multiply it, I get some higher power of n. Okay, so this statement that when summation n is convergent, sorry, summation this root summation of root n times n plus 1 is convergent, that does not imply that the series of an that will converge. Okay, and this is the way we can get the counter example. So was this example okay with you? Okay. Okay, so as I mentioned, like one obvious thing I just mentioned, right, that when you can expect that this series will converge. So I said that if we have some, that the sequence an is decreasing, in that case one can easily do the proof that okay, this statement would be true, and the proof is very obvious, correct? So this is the third problem, that you assume that an is monotonically decreasing. Okay, so with this extra condition on the sequence an, now you can prove that the summation n is convergent. Okay, and the proof I just mentioned, so I'll just write one or two lines. So you know, since an is decreasing, so you can write, so what you have to prove, that summation n is convergent. So first, so what should I write? N plus 1 is less than equal to n for all n, right? Now, so n, if you write, n is nothing but root n times root n. Okay, and this you can replace, sorry, okay, fine, yeah. So root n times root n, now you can write n you can replace by, so let me write this in this way, n is less than equal to an minus 1. So now you can replace this an by an minus 1, correct, since by 1. Okay, so you've got this. Now you can simply again most important thing, that this is non-negative. Okay, and you know that the summation an, sorry, an times an minus 1, where n is from 1 to infinity, this is convergent. This you know because it's given to you. Okay, so this is convergent, and this so by comparison test, summation an is convergent. Okay, so this was very obvious thing, that how you can get an upper bound. So we were looking for upper bound for this in terms of this kind of term, where you have root and then you have some relation like this, product of two subsequent terms. Correct? Okay, so if you want to match with this one, then I should write an minus 1 first, and then an. Okay, so this is how you can deal with this kind of problem, where you don't have the explicit terms of an. Okay, so whenever you don't have any explicit term, try to use comparison test. Okay, just usual comparison test. Okay, because this was very abstract, you don't know how an is looking and all these things. You just have few information, and from there you have to conclude. So in such scenario, you better use comparison test. Okay, okay, so this was related to this thing. Okay, now let us come to this problem. So you have to check whether this series, okay, whether this series converges or diverges. I think I already mentioned in the last session that looking at the problem, you have to guess like which test one should use. Right? One of you had doubt like which test, when to use with which test. So over here it's quite obvious, right? Because you have power n, then you think okay, nth root might be helpful over here. Correct? So we can start with that test and let's see if that works or not. Right? Okay, so over here an is given as n root n minus 1. Okay, so in that nth root test, you just take 1 by nth power of an and then see what the limit is, or whether that limit exists or not. Like, so you just take n raised to the power 1 by n, then you have n raised to the power 1 by n minus 1. Now this was already, I think, discussed in one of the session, that limit n raised to, so this was two problems as far as I remember, like limit n going to infinity, a raised to the power 1 by n, this is 1, and this limit n going to infinity, n raised to the power 1 by n, this is also 1. Right? Okay, so this was already discussed in one of the session. Okay, so using this you can clearly see that this goes to 0 as n goes to infinity. Right? So you have this limit, so this clearly this limit exists. The limit n raised to the power 1 by n, this is 0, right? And if you remember the test, like the limit, if it exists, okay, then it has to, if it is less than 1, then you know that the series is convergent, right? So now over here we know that this limit n going to infinity, n raised to power 1 by n exists, and this is less than 1. So the series given to us, which is summation an, this is convergent, right? So this was very easy problem, where we actually the limit also existed. But if limit does not exist, you have to check that whether you have to deal with basically lim-inf, right, or lim-sup, I don't remember. So basically you have just to make sure that for infinitely, so this is the statement of this root test, right, that if this an, what you have, if this n raised to power 1 by n, this is less than equal to 1, or not maybe less than 1. Okay, or you can write it in this fashion, maybe less than equal to r, where, or just write this. So when you have this for infinitely many n's, then the series an is convergent, right? This is the more general statement. And if this n 1 by n, this is greater than 1 or even equal to 1, so after some nth point, so this for infinitely n means basically that after some stage. Okay, so even you can replace this by something like this. So for maybe n greater than equal to some k naught, and here also for n greater than equal to k naught. If you have such thing, then in this case the series will diverge, right? So if you have get some k naught existence, then you are done. I mean, in case the limit does not exist, in that case you basically have to find some sort of subsequence. So you can deal with lim sup or lim inf, right? And to get the existence of some subsequence which is converging uh, to some limit which is strictly less than 1 or greater than 1, this kind of thing. Okay, if you get one of the cases, then it's done. Okay, so you basically have to get this kind of bound, that's it. Okay, so let's move to the next problem. So like I should mention, like in this case you can, so using lim inf you can get the lower bound. So this can be lim inf, so finding lim inf of an, and here you can use lim sup. Okay, so if lim sup you get that lim sup is less than 1, then you are done. And if you get lim inf is greater than 1, then it's also done. Okay. Okay, so now let's come to the next problem. So over you have been given that suppose this n is a sequence which is monotonically decreasing, okay, of positive numbers, such that this series is convergent. So n is a decreasing sequence, n's are non-negative, then you have, oh, not non-negative, it's basically positive. So positive means, so this basically means strictly greater than 0 for all n. Okay, then you have to prove that the limit of n goes to 0. So you already know that. Okay, so suppose you have this condition, right? When n is convergent, then you know from here that n goes to 0 as n goes to infinity, right? This you have seen this result, correct? This is the necessary condition for a series to be convergent. So this sometimes helps, right? So if you want to prove basically that some an is not convergent, suppose you want to prove this, then you first check that whether limit n equal to 0 or not. So if it is not equal to 0, then you can immediately say that the series is divergent, right? And if it is 0, then you cannot conclude, you have to check for, you have to go for some other test. But this is the primary thing what you need to check. If you see that the limit is non-zero, then you can directly say that the series is divergent, right? It's not going to converge. Okay. Okay, so this is one of the necessary condition for the series to be convergent. Over here what you have been, there are few things which is extra, right, which is given to you. The first thing is that it is decreasing sequence, and the second thing is that it is positive, like the sequential terms are positive. So n is greater than 0. Now you have to conclude that this n times n will go to 0. Okay, so so let me think of some immediate example. Okay, anyway, 1 by n will not work. Okay, anyway. Okay, so now the question is how to prove this. Okay, so do you remember the proof, like how this was proved? The proof was very easy, right? So can you recall the proof of this one? Because it is based, the proof of this problem is based on the idea which was used to prove this statement. So can you recall the proof? Anyone? No? Okay, so I'll just sketch maybe. So see what you do. So when you know that this series is convergent, okay, so let me just write one or two lines because the proof is same. Okay, so suppose this is there. Now you define the nth sequential term. Okay, the partial sum like this. Okay, then what is this Sn plus 1 minus Sn? If you take the n plus 1th partial sum and you subtract the nth partial sum, so what you get is a capital N, right? This is what you get, right? Now if you know that this sorry,
A n plus 1 is not.
oh sorry, this is an plus 1, sorry. So this is an plus 1. Now you know that this sequence of partial sum, since this series is convergent, so limit Sn exists, correct? So like if you want, then suppose that this series, so what should I write? So let me denote it by S. Okay, this series, so this series converges to some real number which is S. Then if you take limit over here, so what you get if you take limit n going to infinity? Okay, so if you just want to n, then let's write it in this fashion: Sn minus Sn minus 1. Okay, now if you take limit over here, so limit n, this will be S minus S, which is 0, right? So this is the way you prove this statement, right? Correct. So what we'll do here, just copying this idea, we'll try to prove the first statement. Okay, and then we'll look for the converse, I mean the B part. Okay, so let's first try to prove the first part. Okay, that the limit n times n will go to 0. Okay, so the proof is like this. So see, you over here, what did you get? You get n, and what you use? You just use the difference of two consecutive nth partial sum, right? Now when you want to get n times something, you should expect, like we should try to take difference of, like where we get n terms, right? So what I mean is, so suppose if I do Sn plus 2 minus Sn, if I do here, I will get an plus 2 and an plus 1, right? So here I am getting two terms. Okay, note that we have this decreasing property as well. That is very important over here, because now when the sequence is decreasing, what I can do here, what one can do, or maybe greater than equal to, because I have the lower bound that it is greater than 0, so I just need to get lower bound. Okay, let me see. So if it is decreasing, then I can write this is 2 times an plus 2, right? Because an plus 1 is greater than an plus 2, right? This is how we can define decreasing. Or if you get upper bound, you can write 2 times an plus 1. So this kind of bound we have. So here I am getting 2, and this is kind of an kind of thing, right? So this motivates us to write it in this fashion. Okay, so this is the idea, so which is similar to the previous one. Okay, so now what we can do is, now we will subtract n elements. So what I will do, I will take S2n and then I will subtract Sn. Okay, just the double. So what is the difference? The difference would be A2n plus A2n minus 1 plus dot dot plus an plus 1. right? This is the difference what I get. Now how many terms are there? Here you have n terms, correct? And over here, since n is decreasing, you can bound each of these terms, okay, with this, because this is the lowest term, because it is decreasing. So a to n, I'll have the least value. So here I can write this as n times a to n. Okay. Right, and I know that this is greater than 0, positive thing is there. Okay, so what I have got is n times a to n is less than equal to s to n minus s of n, and this is greater than 0. Okay, now if I pass the limit, then by Sandwich theorem, what I get is limit n going to infinity, n times a to n is equal to 0, right? Is this okay? Now what do you think? Does this solve the problem?
But there they have mentioned n into a n, not a to n.
Correct. So what do you think? What should we do next? So here what we have proved is that it's still not a subsequence. So what I can write from here is, if I multiply this by 2, then also it's true. So I will get 2n times a to n is 0. So I have got that one subsequence, which is the even subsequence, is going to 0, right? Now can you tell me like how to prove that the actual sequence goes to 0?
If the sequence is convergent, then it converges to the unique limit, sir.
Yeah, that is true. But so far what I have proved, that one subsequence is going to 0. But that does not prove that the main sequence also goes to 0.
You have to consider another complementary sequence.
Another, which one?
2n minus 1.
Okay, you are saying, okay, complementary, right? So the odd one, right? So let me recall one of the problem that we dealt. So this was one of the problem which was discussed, maybe I don't remember the number of session, which session it was, but okay, it was like, suppose you have these a to n and a to n plus 1. Okay, if these both subsequence are convergent, and the another thing was that a to n, the limit is same as this 2n plus 1th limit. If you have this criteria, then this implies that the sequence an is convergent and limit n is same as these limits. So let me say this is L or something. Just put it right. So suppose this limit is L, then this will also L. Okay, so this is the theorem what we'll try to use. So over here what we have shown that one of the subsequence, which is the even subsequence, is convergent. Now we have to prove the odd one. So again we can do the similar trick, right? So over I have used this 2n to get here 2n, right? Because I wanted the maximum one. So now I'll do 2n plus 1, correct? Okay, let me write here 2n minus 1, then it would look good. Although like the first terms does not matter in the convergency, but okay, let's write 2n minus 1 for the completion. Okay, so over here I'll do 2n minus 1 then. Is 2n minus if I do, and if I subtract Sn, so what I get is a 2n minus 1 plus a 2n minus 2 plus an, right? Now I have n minus 1 terms. Like these are n minus 1 terms. correct. Now I can write this as n minus 1, the same thing, times a 2n minus 1. This I can, okay, so just to bring 2, so what I can do is I'll write this n minus half, right, times a 2n minus 1. Okay, so I have just used this one. 1 is greater than equal to half. Okay, then no, this is not a proper bound. Just a second. So what can I use? Okay, so let's use this 2n minus 1. I cannot do, so I just want 2n minus 1 somehow, right, ultimately. So what one can do is n 2 minus 1, I want because if I multiply there, then I'll get 2n minus 2, so I want half somehow. So n minus 1, so this is less than equal to, just a second, so what else can be done? If there was plus, then I can do okay, it doesn't matter much. Not do with minus. Okay, just a second, so let's deal with this one. I don't know, there could be other argument, there should be some argument, I don't know. Okay, so then I'll have this. So I have s2n plus 1 minus sn. Okay, so this is an plus 1 times a2n plus 1. Now this I can replace by n plus half, right? Then I have an 2n plus 1. Okay, so this is greater than 0, so again by squeeze theorem I have that the limit n plus half times a 2n plus 1, this is 0. And now if I just multiply by 2, I'll get limit n going to infinity 2n plus 1 a 2n plus 1, this is 0. So this is the second line. Now using this 1 and 2, one can easily conclude, we can conclude that limit n going to infinity n times a n is equal to 0. Okay. Okay, so one more thing, like since I messed it up, so over here only you can write this line, right? So this would imply that limit n going to infinity, it's the same thing, a 2n minus 1 is equal to 0. So maybe you can write this as 2, like it doesn't matter, because the sequential behavior depends for large n, so it doesn't matter even if you include one thing, right? So here n is, so why I wrote here n minus 2n minus 2, because for n equal to 1, otherwise it would be 3. So just to look it in a better condition, like I just wrote 2n minus 1, so that when you put n equal to 1, it will consider a1. Okay, so let's not forget about a1 in this notation. Okay, so that's why I just included 2n minus 1, but it doesn't matter. Okay, okay, so you have this conclusion. Okay, so see, the idea is similar to this one, what you have done here. So here you just needed a n, so you subtracted 2 nth partial sum. Over here I want to incorporate this n, so I have to subtract with a bigger partial sum. Okay. Okay, so now let's look at the converse part. Okay, so the converse says that suppose you have this monotonically decreasing sequence, okay, such that this limit n times an goes to 0. Now the question is, will the series an, that will it be convergent? What do you think? Do you have any example or any guesses? I think one of the example I discussed in the last session, that example would be helpful. Okay, so the answer is that it's not true, and the example I'll give you this. So see, the if you look at this statement, n times n, this should go to 0, right? This is the first thing, and the second thing is to get counter example that this should be divergent. Okay, now, clearly you know that this kind of example will not work, because this, you know, this is divergent if alpha is less than equal to 1, right? So if you want to meet this criteria, then obviously this will not be fulfilled, right? Because when you put here n times 1 upon n by alpha, so you'll get n up 1 minus alpha, like this goes to infinity, this is not going to 0, right? Because alpha is less than equal to 1. Okay, or when alpha is equal to 1, it will go to 1, so either infinity, this is going to 1 or infinity depending on alpha. Okay, so if you want to meet this criteria, then this won't be fulfilled, so this type of example is not going to help. Okay, but you know one example. Okay, so I'll just write it here. This I need. Okay, so this is the B part, this was A part. Okay, so you want to look for a sequence an such that this n times an goes to 0, but this does not, this series is divergent. So you remember this example, an given by 1 by n times log n. So clearly, like if you take this example, n times n is 1 by n, this goes to 0, right? Sorry, 1 by log n, and this goes to 0. Okay, now how to prove that this summation n is divergent? Do you remember how to prove this is divergent? Okay, I should use n equals to 2.
Cauchy convergence for.
Correct. So here, okay, one more thing, like here n should start from 2, otherwise this log 1 would be 0, so we don't want that thing. So the sequence an over here, what I am defining, is for n greater than equal to 2. So just maybe I should mention it somewhere. Okay, so as you pointed out that we have to use Cauchy condensation test. I mentioned also, like when you get this n kind of thing here, then you can easily understand that we have to use Cauchy condensation test. I mean, that would be the easiest one. So you can clearly see this is infinity, and the reason being this. So this is by Cauchy condensation, and the reason is like this. So this is convergent. Okay, so maybe I should write this. Summation n convergent if and only if 2n times 1 by this 2n and then log 2n is convergent, but this is divergent, this will cancel out, and this is equal to summation n times log 2. Okay, this is convergent, but this is not. Okay, so this is not, so this is not. since this is not true, this is not true. Okay, so this was the answer to this problem, the converse. So the converse is not true. Okay, so now let's come to this problem. Okay, so this was fine, no? Any doubts you have? Okay, so now let's move to the sixth problem. So over here you have to check the convergency of this kind of series. So although I have mentioned here that you use the ratio test, but if you can think for some other test, then that is also possible. Okay, so over here we will try to use the ratio test. Okay, so let's begin with the first problem. So here if you notice, this an is given by xn upon n, right? So now for the ratio test we just need to evaluate the ratio of an plus 1 upon an, right? So the ratio an plus 1 an, this is equal to xn plus 1 n plus 1, and then you have n times xn. So this is x times 1 upon 1 plus 1 by n. Now if you take limit, clearly this limit exists, and if you take the limit, what you get is x, right? So so you know that when the limit is strictly less than 1, then you know that the series is convergent, right? So the series an is convergent if, by ratio test, okay, if x is less than 1 and the series an is equal to infinity if x is equal to 1, sorry, x is greater than 1. So this is by ratio test. Okay, but you cannot conclude about x equal to 1, right? So you just simply put x equal to 1. So for x equal to 1, summation an is nothing but summation 1 by n. And this is clearly divergent. Okay, so the answer is that this converges if and only if x is strictly less than 1, right? Okay, this was too easy, nothing, you don't have to do much for this test. Okay, now let's move to the second part. So the second part is given in this form. So if you look at this part, what is this? So this you can write it as, so this is n upon, okay, let me write 1 plus, this is summation n from 1 to infinity, and then you have n raised to the power n upon factorial, right? This is how this series can be written in a shorthand notation. So I'll just cut this one. Okay, so this is your series, right? So over here, like, we don't need to care about this one, this is okay, this is finite, so we just need to worry about this series. If this is convergent, the whole series is convergent, there is no issue, this is just one term. So over here we just concentrate on this sum. So you have an is given by n raised to the power n upon factorial n. So let's try to see the ratio an plus 1 upon an. So you have n plus 1 raised to the power n upon n plus 1 factorial, and then you have n factorial upon n raised to the power n. Oh, so here it would be n plus 1. So if you write here, so this is n plus 1 times n plus 1 raised to the power n, and then you have n factorial, then you have n plus 1 factorial n raised to the power n. Clearly this cancels with this numerator, right? So what you have is 1, so this reduces to 1 plus 1 by n raised to the power n. Now clearly the limit, if you see, what will the limit of this sequence? E, right? Exponential, and this is greater than 1, right? So by ratio test the given series summation or the given series is divergent. Or you can just write this summation n raised to the power n by factorial n is convergent, and hence the main series is convergent. Okay, so I'm not writing this. Okay, so this is divergent and hence the main series is also divergent. Okay, so this ratio test is very easy to implement. Okay, and in such situation, like you just have to see, like if there is some power of n, like if I do the ratio, if I take the ratio, will I get something simpler whose limit can be evaluated. So for example, in these two cases it was very easy, right? You got this kind of ratio. Here also it was quite easy. You just have to remove the factorial and then you got a proper thing. Okay, so in this scenario you can use it very well. Okay, so heading next to the 7th problem. Okay, so you have to, again, we have a lot of series, like 3 series are there, like you have to check the convergency of this 3 series using the limit comparison test. Okay, so I have just tried to put all the tests separately. Okay, but obviously you can try with some other test also. Okay, it's not that you have to use this test, because like more like this limit comparison test, what is basically the comparison test what you have seen earlier, right? So maybe I can say a few lines on this. So see what you do in limit comparison test. So you have an, okay, so an is given to you, n is given. Okay, so suppose an is given to you and you try to look, so find bn. So the goal is you find bn and evaluate limit n going to infinity an upon bn, right? This is what you do. Now what happens? So these are 3 cases, right? So how should I write? So this is L. So suppose, what are the condition what you get? So when L is not 0 or L is not infinity, so when L belong to R minus 0, okay, then you say that summation an and summation bn converge. Okay, so when you are finding this bn, okay, so when you find this bn, you have to find such bn whose convergence is known to you. Okay, that is important. So you should know that this summation bn is convergent or divergent. Okay, then you can conclude about an. So then the result says that summation an and summation bn converges or diverges together, right? So how do you prove this? I'll just, and when L is infinity or L is 0, you can deal separately. Okay, so the idea is, suppose you have this L, okay, then what can you say? So using this condition, so from this condition what you have, you can basically say that an and bn, this ratio is close to L, right? This is the definition of limit. So L minus epsilon. So this is for large n. So for n greater than equal to n naught, you have this kind of behavior, and this is nothing but saying that you can say this an is bounded by L plus epsilon time bn and bounded below by L minus epsilon by bn, right? Now this is nothing but the comparison test. Now when you know that this summation bn is convergent, you use the upper bound. Then if this is convergent, you use the comparison test to say that summation n is convergent. When it is divergent, you use the lower bound, that this is infinity, so this has to be infinity, right? Because all these are positive, so I am talking about positive sequences. So here an and bn are positive. Otherwise you just take the mod and deal with it. Okay, yeah. So here maybe you can So here I am talking an and bn are positive. But in fact it's true. Okay, anyway, so here I will just write an and bn are positive, but I guess it should be true for any. No, it's true for anyone, but if it's positive you can directly use the comparison test. Otherwise I think, in just a second, L plus epsilon times bn, and then you have L minus epsilon times bn, right? Now when this, if you sum this, it becomes infinity, then this is infinity, so divergence is clear. And now for the convergency, I guess you need the positiveness of an. Yeah, you need it, because then you need some positive condition on an, I feel. Otherwise it won't be possible, because if this series is convergent, like suppose this summation bn is finite, then this summation an is less than finite, but that doesn't mean, if it is negative then it might diverge, right? So you need some an. So this could be minus infinity, for example. So I think you have to include an is positive. Yeah, an has to be positive, otherwise. Okay, so this condition has to be there. Okay. So okay, now let's come to this problem what we have here. So over here you see, let's start with the first one. So one thing is, either you find some bn's, okay, and now how would you find that bn? That is basically based on some bounds. So for example, in this first case, you have this kind of thing, right? Sin 1 by n is like 1 by n when where like this kind of thing you have, that sin x behaves like x when x is very small. That means when n is very large, you have this kind of behavior of sin 1 by n, right? For large n, because this 1 by n is very close to 0 for large n. So that's why, so we'll try look at this as bn. So this would be my bn, choice of bn. Okay, so this is how one can guess like what bn one should choose, and we know that summation bn is going to diverge because bn is 1 by n. Okay, so I'll just write here, so an in this case is my sin 1 by n, and bn I am just taking as 1 by n, right? Then you try to look at this limit an upon bn. This is nothing but limit n going to infinity sin 1 by n by 1 by n. This is same as limit k going to 0. I should not write k going to 0. So, okay, so what is this limit? This limit is 1, right? Do you know the proof of this?
Yes, sir.
How to prove this?
I am logical proof.
No, but yeah, exactly. That's why I removed that thing, right? Because in L hospital you have this continuous limit. So x tending to 0, sin x by x, right? So this x goes to 0 in a continuous fashion. It's not discrete. But over here, this 1 by n is not going to 0 continuously, right? It's like 1 half, then 1 by 3, 1 by 4, and so on, right? But then only here you can use L hospital, because this is for continuous function, or I mean not continuous, but basically you have function which is defined on the real line or interval. You cannot use L hospital for this discrete kind of function. Okay, but this limit will be 1. Okay, and to prove this you can use the epsilon delta definition. It should not be difficult to prove this. Okay, or you can use some bound, maybe like, what can I say, some bound I guess one can use. Let me see. So you have to basically use sin 1 by n by 1 by n minus 1. You have to prove this is very small, so sin 1 by n you will have to use some bound. So this is mod sine 1 by n. Uh, mhm. Okay, but I think I have another proof. So do you know the series expansion? Yeah. Do you know the series expansion of sine x? So this is x minus x cube by factorial 3 plus x5 by factorial 5 and so on, right? So if you try to write sine 1 by n, it would be 1 by n minus 1 by 3 factorial upon 1 by n cube plus 1 by 5 factorial 1 by n5 and so on. Now if you divide it by 1 by n, what you get is sine 1 by n upon 1 by n is 1 minus 1 by 3 factorial, and then you have 1 by n square and then 1 by 5 factorial 1 by n4 and so on, right? Now you know that this will go to, this converges to 1 because this will go to 0, sorry, this will go to 0, this will go to 0 and so on. So this converges to 1. Correct? So this is one proof, although you can use this epsilon delta definition, but over there you have to use some bound. And what bound one can use, I am not getting at this point, but I believe like sine 1 by n. You have to basically show that sine 1 by n minus 1 by n, that would be very small because 1 by n in the denominator will explode. Maybe some bound you have to use. Okay, so at this point I don't know the epsilon delta, this epsilon proof. Sorry, why I'm saying epsilon delta. Epsilon delta is for the continuity, but here epsilon definition basically. Okay, so that, okay, let's forget about this, but you know this is one of the proof which shows that sine 1 by n upon 1 by n, this limit is 1. Okay, okay, fine. Now when this is 1, what do you say? Then this summation 1 by n will converge if and only if summation 1 by n converge, right? Or I mean, I should not write in this way, but okay, just write directly that summation 1 by n is convergent. They show by limit comparison test. Summation sine 1 by n is divergent. Okay. Okay, so this was about the first one. The second one is this example. So here an is given by, let me just write 1 by n log 1 plus 1 by n. Okay, so the first thing you see that the limit is going to 0, right? The limit n going to infinity. Here also one should check, here also I didn't mention it, but you check that limit an, this is equal to 0. Okay, if it is non-zero, then from here only we can conclude that this will be divergent series. Correct? So over here this limit is going to 0. Okay, similarly here if you check that the limit clearly is going to 0. Okay, now again here the question is how to choose my bn. Okay, over here you see this 1 by n is okay. Now what about this logarithmic? How does this logarithmic behave? Okay, so I think one can, without using limit comparison also one can prove, because from there only you can get the idea. So you see this bound, maybe, do you know this bound L1, this bound? Do you know this? Okay, no? Okay, do you know this?
Yes, sir. Yes, sir.
First one you know, right? So this is for x positive, I'm saying. Then from there you can just take log and you can get this, right? Yeah.
Okay.
So these two are the same. Okay. So maybe okay, now from here, why I wrote this, because from here you can guess. So this is also less than equal to 1 by n. Okay, so you can say, okay, so here I think you don't need even limit comparison, but still, so you can write here an is less than equal to 1 by n square, right? And you know these ans are positive, so by comparison test you can say that the summation an is finite, right? Did you get the answer?
Yes, sir.
Yeah, it's easy, no? Like what I just said, you got the point. This an is less than equal to 1 by n square, and you know that summation 1 by n square is finite, so this summation an is also finite, right? Oh, is there some lag? Oh. Okay, now I think it's okay. So this is what I was saying, that summation, so from here only you get the answer. Okay, but let's try with this limit comparison test. Okay, so here, like from here only you can get the idea that my bn would be 1 by n square. Okay, because I have some upper bound by that thing. Okay, so here I'll just write, let me keep it there. So here, so take bn equals to 1 by n square. Now you calculate the limit. So this is 1 by n, this is log 1 plus 1 by n, and you have 1 by n square. So clearly this is n times log or ln 1 plus 1 by n, right? Now you, okay, so this is the limit. This limit n going to infinity. Okay, now you can check that this limit is equal to 1. Okay, now this limit is this one, just a second. So n, and there 1 by n, so it is 1, right? Okay, so this is 1, so therefore this summation bn is convergent, implies summation an, which is summation 1 by n log 1 plus 1 by n, this is also convergent. Okay, but this is unnecessary effort, because from here only you get the answer. So maybe this I can write the second way, and this is the first. I mean, here only you get the answer. This is less than equal to 1 by n square. So by comparison test, summation an is finite. Okay, but anyway, like since in the problem I mentioned limit comparison, so you can use this. Okay, now let's come to the C part. Okay, so this is ln n upon np. So an is ln n upon np. For p equal to 1 you already know, right? Again it's lagging. So can you hear me properly?
Yes, sir.
So there is no lagging, no? In screen I can understand that there is some lagging, I can see, but I don't know about the voice.
Voice is clear, sir.
Okay. Okay, so I was saying that for in this example for p equal to 1 you already know, like just this limit using the Cauchy condensation test you can prove this, that for p equal to 1 it was divergent, right? It was easy proof. Okay, by limit comparison. So now we'll do for general p, or we'll try to see when it is convergent and when it is divergent. Okay. Okay, fine. So over here what would be our bn? That is the question, right? Because in the condensation test, okay, so maybe you can just try to use condensation test, suppose, then what will be the answer? So this is finite if and only if this summation 2n times ln 2n upon 2n raised to the power p is finite, and this will cancel out, so you will get 1 by 2n raised to the power 1 minus p. So this is n, sorry, n times ln 2 is finite. So see, when p is greater than 1, okay, then just a second, am I correct? Okay, so you can clearly see when p is equal to 1, okay, then this is going to diverge. So this is going to diverge, that is obvious. Now for p which is less than 1, again it is divergent, correct? That is, just a second, so 2n and n log 2, 2n will cancel, so I'll have 2n p minus 1, this is n. So this is n log 2.2n p minus 1, this is finite. Okay, so for p equal to 1 it is clear that this, so let me write, so p equals to 1, this summation n log 2 n ln 2 upon 2n p minus 1 is going to infinity, right? Because this denominator will not be there, and then you get the divergence for p equals to 2, oh sorry, now if I take p to be greater than 2, sorry, greater than 1, then this summation n log 2 to n p minus 1 will be so this will be convergent, right? This will be convergent, correct? And now when you take p to be less than 1, because this 2 raised to the power n will have higher power, I mean the growth of n, I mean I think in one of the I mentioned this also, that the growth of n is less than growth of 2 raised to the power n. Okay, so that's why this, you can check that this is convergent. And for p less than 1, you can see this is n ln 2, and then you have 2n 1 minus p, so you can write this as 2n 1 minus p, that means 1 minus p would be positive, and then you have n, you have ln 2, and this is divergent, because if you take the limit of this thing, this is not 1, so it's not 0, so limit n going to infinity, n 2n 1 minus p, if you take, it is infinity basically. You can check that this is infinity, so non-zero, so obviously the necessary condition is failed. So by Cauchy convergence only you can check this convergency, right? So let me call this, right? So just by Cauchy condensation test, this is clear, correct? So this is one way of answering it. So from Cauchy condensation test you can clearly see that this given series is convergent if and only if p is greater than 1. Okay, so this is by Cauchy condensation. Maybe I should write somewhere. This is Cauchy condensation. Okay, but in this problem, like, the question is to use this limit comparison test. Okay, so now you have to use some, you have to find some bn. Okay, and actually you can see, at least from here you can clearly see that it depends on p, like what is the power of p, that will determine whether the series is convergent or divergent. So in the same way, depending on the value of p, one should expect bn. So if my p is equal to 1, what will be the bn? If p is greater than 1, what will be the bn? If p is less than 1, what will be the bn, right? Okay, so we'll try to find bn depending on the value of p. Okay, so let us say, so let us begin with one of the cases. Case 1, let's say when p is less than equal to 1. Okay, so okay, although I know that this is going to be divergent, but still, so for p less than equal to 1, I am taking this bn to be 1 by n. Okay, and why okay, so just look at for p equal to 1. Okay, let's just look at p equal to 1. Then you can clearly see when p is equal to 1, my an is ln n upon n. Clearly my goal would be to take bn to be 1 by n, so that when I do an upon bn, okay, so I'll get ln n, and which is infinity. Okay, so now this is infinity, and this will tell me, okay, so this limit, and I should write this limit n going to infinity, an upon bn is infinity, and this tells me that an upon bn is greater than equal to k for large n, right? And this will tell me that an is greater than equal to k times bn. Okay, so although in the limit comparison test you have, when it is infinity, what is the scenario, I am just giving the proof. Okay, so this for n greater than equal to n naught, and this will tell you that since summation bn is divergent, this will imply that summation an is divergent. So I am doing this for p equal to 1, but the same thing will be done for p greater less than equal to 1, nothing difference, but still, so for p equal to 1, my an was this. Okay, bn is 1 by n, an by bn is this. Okay, and the limit is infinity, which means this, and which means this, and now you, from here you can conclude that summation an is going to be infinity. Okay, is this fine? Yeah, okay, now when you have this p, I mean p is less than equal to 1, what will be the bn? You just take the same, so what you do, now you choose bn to be 1 by n raised to the power p. Okay, so an is this, bn is this, and the same story, right? And now you know that summation bn is, so and summation bn, which is equal to summation 1 by n raised to the power p, is divergent for p as p is less than equal to 1, and so this implies an is divergent. Okay, so the proof is not different, it's the same. Okay, so this was the case. Okay, so this bn I should remove, I'll just copy this. Okay, so this was the case 1 when p is less than equal to 1. Now how to deal with this case 2? Okay, when p is strictly greater than 1. Okay, here you have to do a bit of manipulation, but it's easy only. So when p is greater than 1, that means p is 1 plus something, right? So here p is greater than 1 means p, I am writing this p as 1 plus some q. Okay, so q is some positive quantity, obviously some fixed quantity. Okay, so P I can write like this. Now what I'll do, I'll choose my Bn, okay, as 1 by n 1 plus q by 2. Okay, and why I'm doing this, like it's going to be clear, because when I'll write this an upon Bn, you will see that because I have to calculate the limit of an upon Bn. So from here you can clearly see that this summation Bn is finite, right? Because this is, the power is greater than 1, so this summation Bn is going to be finite, that is for sure, right? Now let us try to see the limit. So an upon Bn, if I do, I'll get, so what was n? ln n upon n raised to the power p. But what is p? P is 1 by q. Okay, and then Bn is n 1 plus q by 2. Okay, now you can see like why I have chosen q by 2. I mean, you can even choose q by 4. That's not a, but you have to choose something which is less than q because this power of n should be in the denominator, so that the growth of logarithmic does not dominate. Okay, so you see, so this is ln upon, this is n, so what will be this? This will be q by 2, right? This is the value of an upon Bn. Now if you take the limit, what will the value of limit? So see, the log n, the growth of log n is very less. Like you can make it, you can bound it by any polynomial growth of n. So why? So you can see by this example. So how should I say? So you see the exponential, okay, exponential of root x. So for example, I'm just stating the example. You know that exponential of root x is greater than equal to, what should I say, some constant time x, right? So like if you write the expansion, it will be 1 plus root x plus x by factorial 2 plus dot dot dot, right? And you can dominate this by 1 by 2 factorial or 1 by 2x, correct? Now this would mean that e root x is greater than equal to half x. Now if I take the log, I'll get root x is greater than equal to, so you can do one thing, you just take 2, what you can do is, okay, let me take the log. So log is root x greater than equal to log x minus log 2, right? So okay, so you can say log x is less than equal to root x plus log 2, right? Okay, we don't care about this log 2. Okay, so what I am trying to say, see from here, and then I will generalize this. So this log x is less than equal to some x raised to the power half plus something, some constant, right? Log 2 in this case. In the same way, what you can do is, you can start with e x raised to the power alpha, where alpha is any positive, alpha belong to 0 1, so maybe I should write, so for alpha belonging to 0 comma 1, okay, you can write e x raised to the power alpha as greater than equal to some constant time x, right? Because like but will it be true? So just a second, because if alpha is non-rational, then we cannot say. So let's take x, alpha is rational, okay? So alpha is some fraction, so let's take alpha is 1 by n kind of thing. So let me write in this fashion, e raised to the power x by 1 by k, okay, for some k. Then I can say this is greater than equal to c times some x, because at kth level, if I take kth power, more precisely it would be 1 by factorial k x raised to the power x, right? And now again you take the log, so what you get is log x is less than equal to x 1 by k plus log factorial k, right? So this is just a constant. Okay, so what you can do here is you can write this log raised to the power n. Okay, you can bound this by n raised to the power some, so okay, q by 2, so q by 2 is a rational number, right? I should not say rational. Okay, so I can say that q by 2 belong to a real number. Okay, and in fact it is greater than 0. So q by 2 is greater than q by 2 is greater than 0. This means by Archimedean property you can find n large such that 1 by n naught or 1 by n is less than q by 2 for all n greater than equal to some n naught. Okay, so this is by Archimedean property I can say this. So just a second. Yeah, maybe I should put black only. Okay, so I have this n. Okay, so what I'll do, I'm using this n, so maybe I'm using n naught. So now using this 1, okay, so using this 1 I can write this log n by n raised to the power, so let me write here k just for the proper notation. So n raised to the power 1 by k plus log c upon n raised to the power q by 2. Okay, so what will happen now, I can write it further as, so this is n 1 by k minus, or in this fashion should I write 1 by n q by 2 minus 1 by k, and then plus log c by n raised to the power q by 2. Now if you take the limit, okay, so again by sandwich theorem I'll just write directly, because you see this power what you see here, this is positive. Okay, so by sandwich theorem or squeeze theorem, this limit of a and bn will be 0 because this is a positive quantity. Okay, but I mean I'm just giving this proof, so it's becoming a bit bulky, but once we accept this fact that this limit is equal to 0, then there is nothing much to do. Okay, so the main trick over here is to finding this bn, and bn is you take some power of n which is less than p, frankly speaking. So even if you forget about this whole thing, I am taking an is what, an is my ln n upon n raised to the power p, and my bn is nothing but 1 n raised to power q, where q belongs to 1 comma p. Okay, so it's less than p and greater than 1. That's the important thing. Okay, so in crux I can say this. So this is the whole crux of this proof. Okay, and now you have to do a bit of mathematics. Okay, so clearly this summation bn would be finite, and the limit an upon bn will become 0, like using the same argument, nothing special. So now the main thing is that when this limit is 0, so by limit comparison test, and this summation bn is finite, so by limit comparison summation an is finite. And why I'm saying this, you can just prove it easily, because this limit is 0 means that an upon bn, okay, this is less than epsilon, right? This is less than epsilon. Okay, and now you can say an is less than epsilon times bn, and you know that this series is convergent, so this is convergent. That's all, because this is positive. Okay, and I think here I didn't mention that you see this sine 1 by n is also a positive thing, right? Because it's very close to, so sine graph is how this sine graph is like this, right? So sine 1 is somewhere here, maybe, I mean this value, right? Sine pi 1 is always in this region, maybe. So this sine 1 by n is always in this region, so sine is always positive, so this n is always positive. Okay. Okay. Okay, so this is the main thing to keep in mind, that I am choosing Bn is 1 by n by q, where q is from 1 to in between 1 and p, and this will solve the whole issue. Okay. Okay, so this was about this limit comparison test. Now let's move to the next problem, which is this one. So over here you have to check the convergence of this particular kind of series. Like how to write this, it might seem you must be looking at for some pattern, and it's very easy to see the pattern. So if you see this odd term, these are just even powers of 1 by 2, and if you look at the even terms, these are just odd powers of half. Okay, so in summary, what I can write this as, so this is summation 1 by 2 raised to the power 2n, where n is from 0 to infinity, and the other one is summation 1 by 2 raised to power 2n plus 1, where n is from 1, right? So this is the series which is given to us over here. But how to okay, but I think from here only you can conclude. Right? Can you see the proof, like just from here? In fact, like you can just simply combine this. Okay. So this is nothing but summation 1 by 2 raised to the power k, where k is from 0 to infinity, right? Okay. Okay, so I mean, so do you know that this series is convergent? This geometric series and all? This you must be knowing, right? Yeah? Correct. Okay, so although you know this, but okay, then we'll try to prove it in a different way. I mean, we'll try to prove it basically. So for this particular problem, we'll try to prove that this series or this particular geometric series is convergent. Okay, and how to prove this? Okay, so the solution would be like this. So suppose this is my S, I'm writing this as this. So this is clearly a positive series, so it is 1 by 2 cube. So this is just a rearrangement. Okay, that is the important thing. So this rearrangement, so this I have written that this is equal to this, but this I can only write when I prove that this is convergent, right? This is I mean absolutely convergent and all, because you cannot do rearrangement of things and you cannot say that they are equal. Okay, so I should not write this. This is a wrong statement to make initially, but eventually you can write that, right? Because rearrangement you cannot do always, right? If the sequence series is conditionally convergent, in that case each rearrangement might give you different value of the series. Okay, let's not go into this, go into that, but you cannot write initially as this. Okay, so I did a mistake over here. I should not write directly in that fashion. Okay, so let's look at the series directly. This is 1 by 2 cube, 1 by 2 square, 1 by 2 5, okay, 1 by 2 4, and so on. Okay. Okay, so now we without rearranging it, we'll try to look for a pattern. Okay, how can we write the nth term of this series? So we are not allowed to rearrange the stuffs. Okay, then you see, I'll write again. So this is 1 by 2 raised to the power 0. Okay, so this is the first term, so I can write this as 1 minus 1 maybe. This is the second term, so this is 2 plus 1. So maybe why am, so this one, okay, let me write completely, then I will say. Okay, this is the third term. So third term I'm writing 3 minus 1 because the power is 2. This is the fourth term, so I'll write this as 1 by 2 4 plus 1. This is the fifth term, so I can write 5 minus 1 and so on. So what I have done, so this for odd position term or even position term I am subtracting 1, and for even, sorry, for odd position term I am subtracting 1, and for even position term I am adding 1, right? Because this is the second term, so I am adding 1. This is the third term, so I am subtracting 1. This is the fourth term, so I am adding 1. So what I can write here is, this is so let me write, this is summation n from 1 to infinity. This is 2. So the first thing is that I'll write the position, the power what I'm getting. So here, for example, this second term, first term, third term, fourth term, fifth term. So the first thing is 2 raised to the power n. The second term is, depending on what my n is, it will have plus 1 or minus 1. So I'm writing this is plus minus 1 raised to the power n, right? Now it fits, because when n is odd this will be negative and then you are subtracting 1. When n is odd, n is even, then you are adding 1. So this perfectly, you can write this s in this fashion. So let me not write s. So this series can be written in this way. Okay, now you have to use some test. Okay, so can you think of some test, like what test one should use? Any idea? No? So see, over here you have some power of n, right? In that scenario, what do you use? So here your an is 1 by 2 raised to the power n plus minus 1 raised to the power n. So what one should use in this situation? We have already used this kind of thing, right? When you have some power n, then you try to use first the ratio test, nth root test, right? So you just take limit. So clearly this is a positive sequence. So limit n, if you do 1 by n, what do you get? 1 by 2 raised to the power 1 plus minus 1 raised to the power n upon n, right? This is what you get if you take the 1 by nth power of this term. Then clearly this limit is going to be 1 by 2, and this is clearly less than 1. So by ratio test, by nth root test, summation n is finite. So this, the given series is convergent. Okay, I hope this is clear. If you don't have any confusion, I can proceed then. Okay, now let's come to the next problem. So this is not that difficult, but you just have to notice one thing. Okay, so the only thing what you need to notice is what is 720. So can you write this 720 in as a factorial of some natural number? What is 720 in some factorial? What is 5 factorial? Okay, start with the first one. What is 3 factorial? 6, right?
So,
Yeah. What is 5 factorial? Okay, 6 factorial, right? So 720 is 6 factorial, right? Correct. Now I think you can get the answer. Okay, so an is what? An is sine n factorial pi upon 720. Correct. Now if I take, if I try to find what is a6, so a6 is going to be sine pi, which is 0. What is a7? A7 is
7 pi.
7 pi. So again it's 0. So you can clearly see like an is equal to sine n n minus 1 till 7 pi for all n greater than equal to 7, right? So what you see is that this series is nothing but a finite sum, because after 6 it is 0. So this is nothing but, so summation n from 1 to infinity is nothing but summation n where n is from 1 to 5, because after 6 it is 0. So it is just a finite sum. Okay, so this is a finite number, so this is a finite sum. Okay, so now let's look at this problem, 10th one. So over here what you have is, you have been given this a1 is this, and this an plus 1 is defined recursively, and then you have to find the value of an inverse. Okay, so see, in this situation what you basically try to do is, obviously you cannot use any test and all, because you have to find a value, because by test you just indicate whether it is convergent or not. Okay, over here you have to find the value of summation 1 by n, and such problems have already been discussed in the last sessions, where what you try to do is, using the recursive relation, you try to find the partial sum as some telescopic sum, right? And then you try to see like where it converges. Correct? This is what we usually do when you have this type of question. So over here my goal, or our goal, should be to write 1 by an as something in terms of n plus 1, right? This should be our goal. So let's try to see, like using this relation, what we have. So you have been n plus 1 is n square minus an then plus 1. So clearly this can be written as an minus 1 plus 1. So you can write n plus 1 minus 1 as an minus 1. Okay, so now you have to write 1 by an, right? So what one can do is, you see, you can see some pattern that n plus 1 minus 1 you do, and n minus 1 you do. Correct? So now we need to find this 1 by n, so we'll just take the reciprocal and then try to see what happens. Okay, so this now I can do is 1 by an plus 1 minus 1. So from here we can see that there is some pattern. Now I'll take reciprocal, so I'll get an and then I'll get an minus 1. Now again, like as I mentioned, how to write it as sum. So you can write it as 1 by an minus 1. So when you put an equal to 0, you will get minus 1 here, and then this would be plus 1. Correct? Okay, so now you can write this 1 by n as, so 1 by n can be written as 1 by an minus 1 plus, minus 1 by an plus 1 minus 1. So this is how this 1 by n looks. Okay, and you have to find this infinite series. So let's try to see what is the finite nth partial sum. So n equals 1 to capital N, 1 by n if I try to do. So again there will be a cancellation, right? So So if I put n equal to 1, what will I get? I will get 1 by a1 minus 1 plus 1 by minus a2 minus 1 plus 1 by a2 minus 1 minus 1 by a3 minus 1 plus 1 by 1 by a3 minus 1 minus 1 by a4 minus 1 and so on, and at last I'll get 1 by an minus 1 minus 1 by an plus 1 minus 1. Okay, now you can see there is a cancellation, like this will cancel with this will cancel with this will cancel with the next term, and this will also cancel with the previous term, right? So in between there will be no term. So what I am having is, so this a1 was given to be 2, right? So I'll have this 1 by 2 minus 1, which is 1. So this is 1, and then you have minus 1 by an plus 1 minus 1. Okay, so this is the partial sum. So maybe I should give a number to this. So this is summation 1 by an, where n is from 1 to capital N. Now you see, in this problem you have to see that how my sequence an behaves. Okay, so if you know that where this sequence converges, then you know the value, then you get the answer, right? So now my claim would be, like my job would be to find how this sequence behave. How does this sequence an is behaving? Okay, so now first thing is, like what you can notice is that, see, the sequence is increasing, like so a1, if I put 2, okay, let's not say in that way, but see, an plus 1 is given as an square minus an plus 1. Okay, so let's forget about this one. We don't care about this one as of now, because this is a positive term. Okay, that is not depending on n. What you see is this an square will increase rapidly, right? So this an square is always greater than equal to an, because like ans are, so because of this, so because a1 is greater than 1, so a1 square is greater than a1, right? Similarly, a2 is greater than a2 square is greater than a2. Okay, right? So you can clearly see this n plus 1 is increasing. Okay, if you want a proof, I can give. Okay, let me be a bit quick. Okay, so this was about this. Okay, so this is what we got. Now what we can do is, see, a1, you know that a1 is given to be 2, which is greater than 1. Okay, now an plus 1, it was an square minus an plus 1, right? And now you want to see whether it is increasing or not, so you take the difference. Okay, but this, what I said, is the observation, and it's from there it's very clear that this is going to be increasing. Okay, so if you try to see this one, then you will get an square minus 2an plus 1, right? And this is nothing but an minus 1 square, and which is greater than, in fact this is greater than 0, strictly greater than 0, right? Because a1 is greater than 1, so it is positive. So a2 is strictly greater than a1, a3 is strictly greater than a2, and so on. So this would imply that an plus 1 is strictly greater than an for all n. Okay, so this is an increasing sequence. Okay, now suppose that this is bounded. Suppose, so this is assumption. Okay, suppose an is bounded. Then what can you say? That n is convergent. So by monotone convergence theorem, an is convergent, right? And now you just pass limit in this one. Okay, and let a equals to limit of an. Okay, then you just pass the limit in this identity. So what you get is a is equal to a square minus a plus 1, and this tells you that a minus 1 square is equal to 0, and this tells you that a is equal to 1. Okay, But this is not possible, right? Because I know that each an, okay, so where is it? So an, so here I can write, so an is greater than equal to 2, or I should mention here, yeah, okay, I did. So but an is greater than equal to 2 for all n, and this implies that a should be greater than equal to 2, and this contradicts 1, right? So the sequence cannot be bounded. I mean, this is a contradiction. But so I should put it here. Okay, let it be. So this is 2, this is 3. So 2 and 3 contradicts. So an cannot be bounded. And this means that an, that limit n going to infinity an is equal to infinity, right? So this in the limit, so now from 1, so from 1 what we have is this sum. Now I'll pass limit, so maybe passing limit as n goes to infinity in 1, we get this summation 1 by an, n from 1 to infinity. This is, so this will go to 0, right? This will go to infinity, so this whole thing will go to 0. So this summation would be 1. Okay. So in this problem, like we have done similar kind of problem earlier also, okay, but there we had the explicit expression of an, that's all. Otherwise, other than that, I mean, not the explicit expression, but what I am saying is that in those situations, this expression or this recursive relation was very easy. I mean, it was not this quadratic kind of relation. It was linear, or I mean easier than this one, okay. But over here we have to do a bit. So till here everything is like previous one, like we're just writing this and this, trying to write this 1 by n in terms of n plus 1. We get this telescopic series sum, then we have to pass the limit. Now to pass the limit we have to know where it converges. So we know that it is an increasing sequence, it's very obvious from the expression. So we suppose that okay, it's bounded, then we get that okay, it is convergent, and now I can find the limit. But what we got is that the limit, that it is not convergent, like we got a contradiction. So that means an is divergent, that means an will go to infinity, and so from there we got the answer. Okay, that's it, nothing much. So is this clear?
Sir, in the seventh sum B question, sir.
Sorry.
You have substituted limit n tending to infinity, n into log of 1 plus 1 by n to be 1. How it is?
Where?
Seventh problem.
Seventh, okay.
B part, sir.
Just a second. This one?
Seventh sum. B, second section, sir. B. We approved ABC, 3 things.
Okay, this one. You're
B.
saying how this would be 1?
There you have substituted limit n tending to infinity. 1. Yeah, yes, sir.
Just using the L hospital not in this sequence. Okay, so this is one of the proof. So my claim is that limit x going to 0 ln 1 plus x by x. Okay, now this you can clearly see that using L hospital, because this is 0 by 0 form, right? So now, x going to 0. So this will be 1 by 1 plus x, right, by L hospital, and this is going to be 1. Correct?
Yes, sir.
Now this is saying you that as x goes to infinity, as x goes to 0, this limit will go to 1. Now from this particular case you can say that okay, this is telling me that as x goes to 0, this goes to 1. So in particular, like when my xn, so when I am going through a sequence, so xn going to 0 ln 1 plus xn by xn is also going to be 1, right? This you know, like when you go through a subsequence also, this is going to be verb. Over here you can choose xn to be 1 by n, so you can say limit n going to infinity ln 1 plus 1 by n upon 1 by n is 1.
Yes, sir, understood, sir.
Okay, so this is one way, although this is not the proof what one can what one should do when you are doing real analysis. Okay, you should try to prove it by definition. Okay, and that could also be done. So that maybe I'll try. Just a second. So you have n ln 1 plus 1 by n minus 1. Okay, you have to show that this is very small. What you can do is, what I can see is again the series expansion, but I don't want to go to the series expansion thing. Again, the other proof would be that you just expand ln log by series in terms, like use the series expansion of log and then multiply by n, and then you can see that it is going to be 1 if you pass the limit. That is another proof, but using this epsilon business, I don't know how to prove it. I mean, these are very standard limits, so, but how to prove using epsilon definition, I cannot see any way as of now. I don't know. Now I can only, what's coming to my mind is like just to use the expansion of log, you subtract 1, you will get 1 by n or something, and that can be made very small. Okay, this is one of the argument that I'm thinking of. Okay, but I still, because you cannot use triangle inequality and all. See, the main goal is to make this quantity very less than epsilon, and you cannot use triangle inequality. So I think the only way to do is that you can use the series expansion, use the series expansion of log 1 plus x. Okay, and then you subtract minus 1, you will get something 1 by n raised power something, like alternating thing. Okay, and this you can make it less than epsilon. So that is another proof. Okay, so using epsilon definition, but obviously you will have to use the series expansion. Okay,
Yes, sir, thank you, sir.
do you have any other question? Okay, then that's it for today. See you next week then. Okay, bye.